everyone, today we'll be starting on chapter 19, quantum physics of the physics book. Yeah, the physics book. So we have quantum physics over here. Now, why am I doing quantum physics lectures? That is because quantum physics is something that is really, really tiny and not something that you can demonstrate by using a pendulum or any other material or anything like that. No, quantum physics is something that is happening at the very atomic level of physics, and it's something that you can only understand through experiments done by global people. Yeah. Now, actually, before we begin, let's first turn to page 24, which is electronic energy levels in an atom and atomic spectra, because I feel like starting at this level, at this page, would be more effective for understanding. At the human scale, energy values appear to take on any continuous value. So like, let's say I throw my water bottle in the air like this, it will just go up and go down back again. But at the quantum scale, or rather in the atomic scale, electrons around an atom have quantized energy levels. So what quantized means is that it's quantifiable. So what do you mean by quantifiable? Everything is quantifiable. No. All of these are levels of energy that an electron in an atom can take upon absorbing energy. So if, let's say, you give an atom an energy of this much, you'll go back down to this here, n equals to 2. If you give if you give energy of this much, which is just before n equals infinity, you get n equals to 4 over here. This line, yeah, the black line. Electrons can have quantized energy levels, but if they're given an energy that just surpasses the quantized energy level, it will fall back down, and whatever gave the energy can have the remaining energy that's left over. Yeah. Now, there are various ways of inputting energy into an electron. One is by photons, which is a particle of light, which we will learn later. Photons, and one is electrons. Yeah, here, electrons. So there are two ways of giving this Bohr model of the atom its electrons energy, and so it can only have this energy, or this energy level, and nothing else. Remember that, because that will be very important for our very first topic, the photoelectric effect. Now, the photoelectric effect may seem really daunting, but it's really just shining photons on electrons to get electrons out. Pretty straightforward, actually, when you get the grasp of it. It has been theorized that light actually has wave-particle duality, and what this means is that it behaves as both a wave and a particle at the same time. Or not really at the same time, but in some instances, yes. So what is a photon, which we mentioned just now? A photon is a discrete packet or quantum of energy of electromagnetic radiation. So remember, electromagnetic radiation. And this has the energy hf. Now, what is hf? So as I've written down here, hf is h, which is Planck's constant, which is a very, very small constant of 6.63 times 10 to the power of negative 34, times the frequency of the light or electromagnetic radiation, and it will give you the energy inside of that photon. Now remember, a photon is not light, it's electromagnetic radiation. So we can also manipulate it such that we get hc over lambda, because v equals to f lambda, if you remember from your waves chapter, and c is our velocity of electromagnetic radiation, so we get f lambda. And so if we manipulate it just like so, we get f equals to c over lambda, and so we get hc over lambda. Yeah, c has a value of 3 times 10 to the power of 8. Now, if you remember from your electricity chapters, U, which is your electric potential energy, has the value of 1 over 4 pi epsilon naught times qy q2 over r. That will give you your electric potential energy in joules. And if you also remember, voltage is actually Q. Wait, let me just write it down in another space. V is equals to 1 over 4 pi epsilon naught Q over R. So if we times, let's say we're measuring an electron actually, if we times the charge of an electron to get EV, which is actually this value, this thing over here, we will get the same thing, but with another charge over here because there's a charge of the electron, E. And we will get the same thing over here. And that is 1.6 times 10 to the negative 19 coulombs for electrons. And so when we make it into a joule, that will be 1.6 times 10 to the power negative 19 joules of energy. Now, first example, the violet light has a wavelength of 400 nanometers. Calculate the energy of a photon in violet light in joules and electron volts. Now, from the equation above, E equals to HF, but since we only have the wavelength, we're going to have to use this equation over here, Hc over lambda. And so let's just plug that into the equation. H is 6.63 times 10 to the power of negative 4. C is 3 times 10 to the power of 8. We get 3.11 electron volts. As I was saying, 4.9725 times 10 to the power of negative 19 joules. So now we need to calculate the number of photons emitted by 60 watt violet source in 1 second. So if you remember from a very basic chapters earlier, we have 60 watts. 60 watts is energy over time. And since we have the energy of one photon, we can find the number of photons emitted in 1 second, which is energy over time. So that is 60, which is the 60 watts of energy, divided by the energy of a single photon, which will give you the number of photons emitted per time, which is 1.21 times 10 to the power of 20, which agrees with our thing over here. Alright, so what is the photoelectric effect? You've learned what photons is, you've learned how to calculate the energy of a photon, but what is the effect of a photoelectric? That's not how you say it. So the photoelectric effect is the emission of electrons, known as photoelectrons, from a metal surface. So just metal, okay? Metal surface when EM radiation of sufficiently high frequency is incident on it. So if it is not sufficiently high, there will be no emission of electrons. We'll find out why in the next few pages. But here is how it looks like. So when you shine a filament lamp on a emitter, the emitter will emit, and not just anything, it will emit electrons that flow in a vacuum to a collector, and this will drive around a current. Well, rather the current is this way, but electrons flow this way. But they will drive around a current that will be measured on the picometer. Now this current is really small, that's why it's picometer. Yeah, so that's the photoelectric effect. Actually, it's really straightforward. I mean, you shine light at the emitter and there's electrons. It's really fun. But as you know, A-levels is not fun. So here is what is happening. When you place a red filter between the filament and emitter plate at regular brightness. Now, you know that red light has low frequency, right? It has a frequency of 400 nanometers. Now, you need to remember this. 400 to 700 nanometers is around the spectrum of visible light. So yeah, that's the frequency of red light. And so, where is my camera? Okay, hi, I'm back. I don't know what was happening with my camera, but if you remember where I was saying low frequency of red, no current is detected because it is not enough frequency to emit them electrons. But if you increase the brightness, guess what? Nothing happens still, because it is still at the same low frequency. Now remember the definition that we said earlier, it needs to have sufficiently high frequency for current to be detected. And so even if you increase the intensity, there is no current detected even if you shine for a long time. Isn't that pretty weird? Now let's change it to the blue filter this time. Now blue has a higher frequency compared to red's 400 nanometers. Blue has a frequency around 600 nanometers. That's pretty high. Now when you shine blue light, current is detected. In fact, it's detected immediately after blue light shines on the emitter plate with zero time lag at all. This is because blue light has the sufficiently high frequency that is needed for the photoelectric effect. Very nice. Now if you put a blue filter still there, but you increase the brightness, aka the intensity of the light, your current will increase and there's still no time lag. So this no time lag is a common thing among sufficiently high frequencies, so just make sure that you put that there when you're answering the questions. But if you decrease the intensity, current decreases. Pretty straightforward. Now of course, scientists have designed experiments to measure the kinetic energy of the electrons that are emitted by the emitter, because why not, right? So if you put the blue filter on and you make the collector negative, now remember like charges repel, right? So if you emit electrons from the emitter over here and the electrons flow from the emitter to the collector, which is negative, they will experience a repulsion force that will actually just push back those with not enough Ke to reach the collector. And this is how we can measure the maximum Ke of the electrons that are emitted. If you make it more and more negative until, if you read over here, this one is really important, let me just zoom into it. A critical Vxt is reached, guys. Amazing, it became 0, right? So we call this Vs, which is called stopping potential. Now what this means is that even the fastest electrons are not able to reach across this gap over here between the emitter and the collector. So that's why you don't get any current at all. That is the critical Vxt. Now, but if we change it to a even higher wavelength, which is around 700 nanometers, just before ultraviolet wavelength, violet, get it right? It has a higher frequency than blue. It will have the same observation. There will be a V external value that will stop all the electrons from reaching the collector. However, this V external value, of course, is higher because if you remember correctly, which I do, E equals to HF. And so if we increase the frequency, we have more energy, and more Ke means a higher V external. Now this contradicts the wave theory of light, right? We all know that from like superposition, that light diffracts and acts as a wave and all that, but no, it contradicts. Our very first observation is that no electrons are emitted if EM radiation has a frequency that is less than the threshold frequency, regardless of the intensity. So it could be the brightest red light in the world, and it will still have no current flowing. So this contradicts the wave model. Why? Because electrons should have been emitted if it was following the wave model, as long as the intensity is high enough. So why, like, imagine if you just put enough energy onto the electron such that it goes out, that will make sense, right? But in this case, no. In this case, your frequency needs to be red. Sorry, your frequency doesn't need to be red. In this case, the frequency needs to be high enough such that the electrons are emitted. Even if the color of the light they are shining is even more red than the flag that your X has, it's still not going to go out of the metal. However, our next observation is consistent with the wave theory in that rate of electron emission or photoelectric current is proportional to the intensity of radiation. The greater the intensity, the greater the energy per unit area of the EM radiation transferred to the emitter plate. Hence, a greater number of photoelectrons are emitted from the emitter plate. And this is consistent with the classical wave theory. Due to technical difficulties, I will now be recording as a model. Right, so emitted electrons have a range of Ke from 0 to a certain maximum value, and maximum Ke of electrons depending only on the frequency of the EM radiation. Now why is this important? Because when you have different intensity, your max Ke doesn't change. It only depends on your frequency of EM radiation and the metal that you're using. This is because of the work function. So if you remember from your the Einstein's thing just now, the Einstein's photoelectric equation, you have HF is equals to phi plus half mv squared, where half mv squared is your max Ke. Let's say if your phi goes up, which is your metal work function, which goes up, your max Ke will decrease, but because your HF, which is the energy of your photon, is the same. And so your max Ke is only dependent on your frequency of EM radiation. Now, why do they have a range of Ke? We'll explain that later, but you should know that using the wave theory, the electrons should absorb energy continuously from the EM waves, whereas in our particle theory, which we covered just now, it is transferred immediately. So as light incident is light on the metal is increased, energy should be transferred at a higher rate. Notice it's not instantaneous, it's higher rate, and have been ejected with greater Ke. So this observation contradicts predictions made using the wave model. Now the fourth observation, emission of electrons, begins at the instant that the metal surface is illuminated, which means there's no time delay. The wave theory suggests that even at low light intensities, rate of transfer of energy is very low. However, there is still light, and so there should be a measurable time delay until enough light energy has been absorbed by the electrons to overcome the metal ions before emission can occur. So this contradicts predictions made using the wave model because there's no time delay. It's supposed to have time delay, but there's no time delay. Isn't that insane? So these three observations that contradict the predictions of classical wave theory provide evidence for the particular nature of light. And hence, in the next one over here, particle wave duality. So when a photon interacts with an electron of a metal atom, it's either reflected with no reduction in its energy. Now this is important because you have no reduction in its energy in the photon when it's reflected, and you need to know that. Either that or is absorbed entirely by and transferred all its energy to the electron in an all or nothing process. Only one single photon can interact with one single electron, because when your photon interacts with the electron, all the energy is gone. There's no more photon, and so that's why it transfers all of its energy to the electron, and that's why only one photon can interact with one electron. So this is another reason why max KE is different, right? Because sometimes when you shoot a photon, it lands on sometimes you're really lucky, it lands on the first layer of electrons, which is on the very surface of the metal, and so it just immediately goes out with max KE. So that is the ideal case lah, because your KE is the maximum lah. But then if your photon unfortunately lands into, like, say, the second layer of electrons in the metal, it has to bounce off of these other electrons and also the metal cations in order to go out, and that results in less KE. And so you will have a range of KE because not all photons hit like the same layer of electrons like the first one or the second one, and so it has different amount of KE, and hence there's a range. And that is, if I remember correctly, observation 3. Yes, observation 3 of this experiment. So do take note that this is how the photon interacts with the electrons. This is summed up by Einstein's photoelectric equation. I guess I was hallucinating. I did not actually show you guys what this equation was. So what for Einstein's photoelectric equation means is that there's actually a minimum frequency that is present, which is actually given by this little letter over here, and this is actually just the same as HF naught, which is actually the minimum frequency of which is basically the minimum amount of energy required to free an electron from the metal. Now this electron is just freed, right? If you provide the minimum amount of energy, it's just freed. Then your half mv square max is actually just the maximum KE of emitted electrons, which is the fastest ejected electrons. So given in other words, given a light of energy HF, some of it is gone to the work function, which is the amount of energy needed to get out of the metal itself. And then some of the energy is also gone to ejecting the electron over here in your max KE formula. So yeah, that's how it is. That's basically what I said over here. So why are the photoelectrons ejected with a range of KE? So as I said earlier, some of the electrons are below the surface, and hence they also have to collide with the metallic lattice, and so they have different amounts of KE. And some more, I think if you remember from your chemistry, electrons that are closer to the nucleus have a stronger bond with the nucleus because, unlike charges, attract, and so your electrons will be closer to the nucleus and hence experience a greater force. And so more energy is needed to overcome the binding forces and have less remaining as KE. Super self-explanatory. Now let's go on to question 2, where you are given the max KE of the electron as well as the frequency of the incident radiation. Now we can just go ahead and use the formula that Einstein prepared specially for us today, 5th of April 2025 over here, given that phi, we need to find phi, right? Yeah, so HF is basically Planck's constant times F, and F is this. Alright, and so we plus our max energy, which is given to us as 1 eV. Now if you remember from what I said a few minutes ago, okay, maybe not a few minutes ago, it is 1.6 times 10 to the power negative 19 joules. And so calculating that, we should get 3.3725. Okay, apologies for my 7. Times 10 to the power of negative 19 joules. So that is the work function. And this is the amount of energy we need to overcome the binding forces between cations and electrons inside of the metal to get our electron liberated. So when they ask the threshold wavelength of this metal, what do? You simply just put in the formula again, because physics is all about principle, laws, and formulas. So we have E equals to hf, and which is also equals to hc over lambda. Alright, so our E will be this value, and hc is a constant, so we just have hc over our threshold wavelength, and that will give you 5.9 times 10 to the power -7. So apologies, my friend is texting me. Alright, moving on. EM radiation must exceed your threshold frequency. Now this has been proved with the experiments, but let's put it into an equation. So what I've said just now is that your work energy is basically the minimum amount of energy for an electron to be liberated, right? And so we can write it as different ways. HF, which is designated with an F with a 0, also known as F naught. As well as, if we manipulate it further, lambda naught over here. So this is called the threshold frequency and threshold wavelength, which is the minimum frequency and the minimum wavelength respectively for EM radiation to cause photoelectric emission. So this is just overcoming the metal binding forces. But as a result of this, if you remember from your Einstein photoelectric equation, you will get just your HF and 0 KE. So yeah, it's written down here, no kinetic energy, because all you have is just your work function and your HF. I don't know why I'm talking like this. Yeah. Alright, so in this chapter, okay, where to start? Intensity of EM radiation is power over area. So you're gonna need to know how to manipulate your quantities really well, because in this chapter you're going to need it. So your power over area is basically just energy of EM radiation over time divided by area, because power is energy over time. So if you have the energy of a single photon, which is over here HF, and you multiply it by the number of photons, which is n, and given that you already divided by time, you can find that your photons over time, the number of photons over time, is actually n over t, and is proportional to your intensity. So yeah, that's pretty interesting, isn't it? You should know how to manipulate this, because there's a lot of manipulation in this chapter. Why max K is independent of intensity? Because in Einstein's photoelectric equation, there is no intensity written anywhere. And also because the max KE only depends on photon energy HF from Einstein's photoelectric equation. Why there is no time delay? Now, as long as HF is more than this, it will occur instantaneously. And yeah, it will just have enough energy. So there is no like partial transfer of energy or nothing. It's just complete. So once you have that amount of energy, is complete. If you remember from the first few minutes of this lecture, I showed you guys the atomic spectrum, which is like, you know, remember the graph with like the number of with like the energy lines. If you have enough, let's say you need E1 and you're at E0. If you have enough, you can just go away from the metal, right? But if let's say your photons are not energetic enough, the frequency is not high enough, it will never reach E1. And so your electrons will not be able to be ejected, and that is why there is no time delay, because it already has enough energy. Might as well just leave, right? Next up, the worked example 3. Now this is basically just a repetition of whatever was written just now. Just make sure that you memorize it, because there is going to be some questions such as 2007 question where they ask you how to describe the photoelectric effect, how it provides evidence for the particulate nature of this when it's interactive with matter. So yeah, you need to remember that. It's also good for your understanding as well. But I'll skip through that. Work example 4, explain why there is a threshold frequency and a very short emission time provide evidence for particulate nature. As I explained just now, the latter has to do with our atomic spectrum over here. As long as there's enough energy, it can just go out already. And the threshold frequency is basically because it needs a certain amount of energy. So if it doesn't have that energy, it is not going out. And yeah, that is contradictory to wave theory, because any frequency will just give rise to emission of electrons if you have long enough, because the energy will just go like boom, 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 and then like after a long time, it will have enough energy, then after that it will just be out, you know. But that's not the case here, it's particles, so it's all or nothing. Now, work example 5. If you have light or frequency of this, and then you incident on this. Oh, by the way, you don't need to know the work functions of specific metals, just to clarify. It's found that the max Ke is this, and so we can just plug that into our equation to find, given that we have Hf, and we have max Ke, which is half mv square max. I can't bother writing with a mouse. So what we are going to find is the threshold frequency, right? And that is our work function, and our work function threshold frequency is Hf naught. And so we get this answer over here. And if you have memorized your electromagnetic spectrum well enough from, I think, waves chapter, you find that it is in the UV region because it has a very high frequency. Yeah. So since it's more than violet, it's UV. Really simple. Now, in order to measure the max Ke of photoelectrons and stopping potential, which I think we have mentioned briefly earlier in this lecture, we just need to vary the Vxt, but it is important to know how the graph looks like. So when we vary the Vxt, we're talking about the potential of the collector we're talking about here. The collector is important because when you make your Vxt negative, your collector will become negative, and this will repel electrons that are being emitted from, oh wait, sorry, this is not the collector. This is because it will block, or rather repel, the electrons that are being emitted by the emitter. And so you can see over here on this graph, if it is negative, you will have a decreasing current, and this is because at Vs, which is the stopping potential, even the fastest electrons, which means the electrons have the most Ke, are stopped by the repulsion because of the negative potential on this collector. And that is important. Let's say you make it a positive V exterior, you get a saturation current. Now, why is that saturation current? Now, there is an explanation below. Let's jump to B and then move back up later. If it's positive and large enough, it will stay constant. The current will stay constant because it's limited by the rate of emissions of photoelectrons, which is dependent on the intensity of EM radiation. Now, I want all of you to imagine that the intensity is just the rate of photons emitted by your light source. The more photons you have, the higher chance there is of hitting an electron and transferring all of its Ke and resulting in the liberation of it, as well as some Ke left over to go towards the collector. Whereas if you're talking about frequency is the amount of energy that is inside of your photons that allows it to have a higher chance of overcoming that work function, as well as having a higher Ke when it is liberated out of the metal. And so it is dependent on intensity for the rate of emissions, and is dependent on frequency for the amount of energy in the photon. Now at A, I mean, this looks like a really long paragraph, but all it's saying really is that it just has a range of Ke, which is observation 3 from our experimental observations. Because as you decrease the negative potential, you have a largest pushing force back on the electrons, and so your Vs will be when your fastest electron, aka the highest Ke, is pushed back to the emitter. And that is why there is a slope, because it is decreasing. Just remember that it is a slope and not a straight line. Now here's the definition if you want to memorize. Stopping potential is the minimum negative potential needed for you to stop the fastest electron from arriving at the collector plate, and thus just manages to reduce the photocurrent to 0. And that is why it is at 0 current over here, at y equals to 0. Now here's another equation that is really interesting, and something that you also need to remember is that your EVS is equals to your max Ke electron. Why? I believe I've said this a few times already, but your stopping potential is the minimum negative potential required to stop the fastest electron, and this fastest just means that here's the highest Ke. Now the highest Ke is basically then correspondingly equal to the energy that is inputted to stopping the electron, and that is given by EVS. As I mentioned earlier, this is just basically another form of U, and not U as in U, but U as in Ke Q1 Q2 over R, and that is Y is equals to KE, because you need this amount of energy to match this amount of energy to get zero current. Right. Now work example 6. The stopping potential that prevents all electrons from flowing across a certain photocell is 4 volts. What's the max KE given to electrons by incident light? So use this formula and you will get it. Super simple, super convenient. With reference to photoelectrons, what can be deduced from the sloping sections? So the observation is that the current, which is proportional to the number of electrons that can overcome the retarding electric force, decreases as the magnitude of negative PD is increased, because of course you need more force to stop the higher Ke electrons. And this shows that there's a range of Ke. Yeah, as the PD becomes more negative, the number of electrons that fail to reach the collector increases, and so decreasing the current because electrons make current. And so at a certain negative PD, which is your V stopping potential, even the fastest electron fails to reach the collector, and hence your current is now zero because there is no electrons going across that little gap in the vacuum. Right, let's say your intensity is halved. What does that mean? So when intensity is halved, that just means that your rate of photon emission is halved. And you can kind of see in the probability kind of light. I guess if your rate of photons is decreasing, then the chances of you finding a photon interacting with an electron is halved as well. So you're gonna have a lower current when you have a saturation voltage. But do remember that the amount of energy that is being imparted into the electrons is the same because the frequency is unchanged. And so the amount of energy you need to stop even the highest Ke electrons is going to be the same, because even though intensity increases, the amount of energy transferred to the electrons remains the same. Hence, the max Ke remains the same. However, if you change the frequency, it is going to change. So in this case, I mean, if you have frequency constant, then you're just gonna have twice the current when it is saturated, and yeah, that's it because it's only dependent on the intensity. Yeah, if you decrease the intensity by half, it doesn't affect the stopping potential because it is just only affecting the number of photons and not the energy of each photon. So there's a difference in that. Now moving on to example 8. Finally, I've been recording this a few times and finally I managed to reach a new example. Woo! Light quantum of energy 3.5 times 10 to the power of negative 19 falls on the cathode of a photocell. The current is just reduced to 0 by applying a stopping potential of 0.25 volts. Calculate the work function of the cathode. So the work function of the cathode is basically just what is holding it back, right? So if we just plug in our formula, which is HF is equals to 5 plus half mv max squared, you'll be able to find that you already have HF, because HF is given over here, which is your 3.5 times 10 to the power negative 19, and your work function is over here, plus half mv squared max. But we are not given half mv squared max, so we just covered this. Time to apply it. EVS, because EVS is equals to half mv squared max, and then we will get our stopping potential of 3.0975 times 10 to the power of negative 19 joules. Which if you put it to 2SF is this answer, which is correct. Now this equation over here can help you out in formulating a graph if you want to plot Vs over F, but I highly recommend you to just derive it by yourself, because I mean, come on, you're already in JC2, you should be able to be capable of that. And you can ascertain Planck's constant with this, because your gradient will be H over E for any same frequency of light, or different frequencies of light. Yeah, the y-intercept is when your frequency is 0, then you'll be having this intercept over here. Yeah, so I think a clearer graph of understanding for your understanding is here, which is EV over F. So basically the energy that is needed to overcome specific frequencies of light over here, of which the gradient is H. So you can see that this is the threshold frequency over here. So if we continue down, our y-intercept will be the negative of the work function of the metal, because when your frequency is 0, there will be your, yeah, it will be this, I mean, it's in the equation. And this is also a graph of the equation of intensity that you may be able to derive yourself, which is I equals to, or rather I is proportionate to n over t. And n over t is rate of incident photons on the emitter. And so you can derive a graph which is just like that, because current is the rate of photons that is going to go to the collector, and is proportional to intensity. Yeah, so if your intensity is 0, of course you're not going to get any current. If intensity is more, you're going to get more current. Super simple. Now let's say you change metal. Of course, I mean, change metal means different work function. And so it is shown on the graph as different y-intercepts. But notice that your gradient remains the same at Planck's constant. So it must be very important that you draw, if your question asks you to compare two metals, if that you draw with the same gradient. So like kind of like a parallelogram of sorts. Yeah, it's going to be really hard to draw that, but I'm sure you'll be able to do it. So intensity is power of EM radiation over area, which is this thing over here. But again, you can just derive it. I'm pretty sure that the more important one is this one. Because I mean, I don't know about you guys, but I keep forgetting that current is equals to charge over time. And this is important because charge over time is not just for any individual electron, it is total charge over time. So the number of what in this case electrons times the charge of the electrons, which is E over time. So I equals to net, kind of. And if you manipulate it, you will get n over t. To get n over t, you get I over E. Yeah, I over E is n over t. And so if you get I over E, you get n over t. And that is your rate of emission of electrons. Very nice. Very cool. Alright, work example 9. Radiation of wavelength 300 nanometers and of power per unit area 200 is incident on a metal surface. And to calculate the rate of incidence of electrons, we just need to manipulate intensity. So since we have intensity over here, which is power per unit area, and as well as the radiation, which means that we have EM radiation of wavelength 300 nanometers, these two give us our HF. Amazing, wonderful. So using the formula, you will be able to get this n over t is 3 times 10 to the power of 15. And following that, the equation that I mentioned earlier, with current over the charge of the electrons, we'll be getting 2.8 times 10 to the power of 9 electrons per second, which is great because that's the answer. Determine the ratio of A to B, super simple math, just this. Just make sure not to put in fractions though. The emission of electrons and the incidence of photons, rate of incidence of photons on the metal surface is quite vastly different. As you can see, it is differing by 1 times 10 to the power of 6. That's a lot. That means for every 1 million photons, it means that only 1 electron were ejected. Yeah, that's pretty cool. Why? Because not every photon collides with and emits an electron. Most are reflected and scattered by the metal or miss hitting any electron at all, which is actually kind of not very likely. Actually, it's more likely that it's just reflected, because if what this means that it miss hitting any electron is that if it doesn't hit anything else, it just passes through the metal, which is basically just saying that metal is transparent, which is not likely. I mean, no metal I've ever seen is transparent. On the way out of the metal surface, electron may lose its kinetic energy to ions. That means that the work function is too high. Prevents some electrons from overcoming the work function, and so such electrons are eventually absorbed by the metal. Yeah, it's not a good day to be an electron. Alright, now this one is important because this one actually demonstrates a really critical understanding of how a circuit like this works. So let's say we have wavelength of light lambda 1 and wavelength of light lambda 2, as well as MCQs, options that make us determine whether a lambda is less than or greater than lambda, the other one. Yeah. Let's see the first graph. So then the first graph, when E is made positive, we get a we get current. So when E is positive here, we get current, right? So yeah, that's saturation current. We have electrons flowing to F to E. Right. Great. That is lambda 1. Now if we have lambda 2, not only that, we also have the opposite, which is E to F. That means that if there's no current over here, that means that light, its frequency, right, is actually less than the threshold frequency of E. Yeah, that's pretty impressive, right? And so once the frequency is increased, that means that we have current over here. And when frequency increases, wavelength decreases. And we already know that wavelength 2 is actually less than wavelength 1. And that just means that we have these two options over here. Really, really important to understand why this is the case. So make sure to pause and take a understand how this came about. When lambda is greater, that means frequency is lesser. If your frequency of E is higher than, your threshold frequency of E is higher than your threshold frequency of F, is it F? Yeah. Then that means that your work function for E is actually greater than that of F, because you need more energy to overcome the metal E than the metal F. Yeah, because HF ma, so when F is higher for E, that means that the work function of E is higher. Yeah, so the answer is D, and let's check if that is correct, which I know that it is D. Alright, yeah, I'm not reading that sideways. Oh, but this one is important though. You need to know that there is a spectrum, and so what do you expect in this spectrum? So you have your long wave, which is, I don't think you need to know the long wave. You need to know that these are radio waves, infrared, visible light spectrum, and ultraviolet, X-rays, and gamma rays. Right, so radio waves have the longest wavelength and hence the least frequency. The higher you go, the higher the frequency. After your radio waves, your microwaves, you'll have the second longest wavelengths, followed by infrared, then visible light, then ultraviolet, then X-rays, then gamma rays. Gamma rays have the highest frequency, so if you shine gamma rays at a metal, you're probably gonna get like a full-blown current going on. And so yeah, that's pretty impressive. Your visible light is around 400 to 700 nanometers, as you can see over here. I think they printed it wrongly because violet is actually more energetic than red. So this one is actually supposed to be 700 nanometers, and this one is 400 nanometers. Yeah, red has lower frequency than violet. Alright, our next lecture will be on wave-particle duality and de Broglie wavelength. But for now, this will be all for the first lecture. We've covered 2 parts of the series. Actually, not really, just 1 part. But I hope you guys had a better understanding of quantum physics. Thank you for watching.